In this video, we present our paper, MeGAS, Thermomechanical Dynamic Gaussian Splatting for Thermophysical Scene Editing. In real-world settings, temperature, an invisible yet fundamental physical quantity, governs a wide range of visually observable phenomena, from the melting of ice cream to the solidification of lava. Besides, thermomechanical dynamics are among some of the most intricate natural phenomena, since they involve not only deformation and motion, but also heat transfer and phase transitions. In parallel, recent advances in neural scene representations such as 3D Gaussian splatting have revolutionized photorealistic scene reconstruction and rendering from real-world imagery. This naturally raises an important question: can we move beyond static reconstruction and enable controllable, thermophysically grounded editing of real scenes? To answer this, we propose MeGAS, the first framework to incorporate thermomechanical phase change dynamics into 3D Gaussian splatting and enable controllable and thermophysically grounded editing of real-world scenes. Recent studies have integrated physical simulators into neural rendering frameworks. Some approaches embed elastodynamic models into 3D Gaussian splatting to model mechanical dynamics while preserving rendering realism. Beyond elasticity, another works unify position-based dynamics with 3D GS for fluid animation. Besides, some methods synthesize environmental effects such as rainfall and snow within neural rendering frameworks. However, these efforts mainly focus on mechanically driven or purely appearance-level weather visual effects. In contrast, many natural phenomena are thermally driven, where invisible temperature variations govern visually perceivable behaviors such as melting. To address this underexplored yet fundamental dimension of physics integration, we present MeGAS, which constitutes the first attempt to incorporate thermomechanical dynamics into neural rendering framework. Given posed RGB image sequences as input, we first reconstruct the scene with 3D GS. To simulate temperature-driven editing, we propose a thermomechanical dynamic Gaussian splatting representation that jointly models appearance and a controllable thermal field, enabling melting dynamics controlled by phase change, while achieving physically plausible and photorealistic synthesis of thermophysical phenomena from real-world imagery. Integrating thermomechanical effects into neural rendering frameworks remains highly challenging. They require not only momentum conservation, but also the coupled modeling of heat transport and phase transition. Moreover, melting introduces extreme deformations and topological changes, posing a significant challenge for neural rendering representations. To address these challenges, we firstly propose a thermomechanical dynamic Gaussian splatting representation, which couple 3D GS to an MPM simulator with an heat advection-diffusion solver and a phase change-aware constitutive model switching, enabling melting dynamics. To maintain stable rendering under extreme deformation, we introduce a topology-adaptive Gaussian rendering strategy. To obtain a uniform distributed, volume-consistent, floater-free 3D GS, we first augment each Gaussian with a temperature attribute. To drive melting, we require a physically grounded evolution of the temperature field. Instead of heuristically editing, we solve heat diffusion on a simulation grid. Building upon the standard MPM framework, we extend the particle and grid states with thermal attributes. User-specified heat source regions define the thermal boundary conditions, providing direct control over where and how melting occurs. During each time step, particle temperatures are transferred to the grid, followed by thermal boundary updates, and heat advection-diffusion is solved on the grid via a lattice-Boltzmann method. The updated temperatures are then interpolated back to the particles. Once a particle temperature exceeds the predefined melting threshold, we switch its material phase and update the constitutive model accordingly. After obtaining particle-level thermomechanical animation, we map the deformations back to the Gaussian representation for rendering. Since melting entails extreme non-rigid deformation and topology change, naively applying 3D GS under such conditions leads to severe visual artifacts. To address these issues, we further propose a topology-adaptive 3D GS framework. For training stage, we propose a direct yet effective strategy, pruning low-contribution Gaussians, eliminating redundant internal Gaussians. And we adopt an anisotropy regularization that penalizes excessive scale ratios and encourages the kernel to approach a disc-like shape. We further apply scale clamping to prevent large Gaussian volumetric discrepancies. Our regularization produces a uniform Gaussian distribution and reduces internal floaters. Since melting induces extreme non-rigid deformation and frequent topology changes, it causes surface cracking and hollow artifacts. Thus we propose an adaptive surface cracking densification during the deformation process. During MPM evolution, internally filled particles naturally migrate towards surface voids and partially compensate for missing geometry, but they lack valid Gaussian kernel parameters for coherent rendering. To reconstruct a coherent surface representation, we leverage the deformed surface Gaussians to guide the local Gaussian kernel fitting of nearby internal particles. To restore plausible Gaussian kernel for internal particles, we fit an implicit surface from the original deformed Gaussian via implicit moving least squares. Each internal particle is then projected onto the surface to obtain its surface normal, and we assign a new Gaussian kernel to the crack-filling particle. This adaptive densification seamlessly recovers cracked regions with correctly oriented internal Gaussians and yields smooth, stable rendering under extreme melting deformation. We compare rendering quality under extreme thermomechanical deformations with original 3D-GS, Phys-Gaussian, and VR2H. We visualize internal cross-sections and dynamic frames under large-scale melting. Baseline methods accumulate internal floaters, produce severe needle-like artifacts, and suffer from surface cracking that exposes underspecified interiors. In contrast, our MeGAS yields an internal floater-free and volume-consistent Gaussian distribution, with stable, crack-free surfaces refined by our adaptive surface densification. We compare our melting edits against three representative state-of-the-art approaches: DGE, AutoVFX, and Runway Gen 4.5. Prior methods lack physical realism, photorealism, or multi-view consistency, whereas MeGAS preserves photorealistic appearance and delivers physically plausible, temporally consistent melting. We visualize more thermomechanical dynamics of our method under heat diffusion control. As the temperature field propagates through the object, phase change-aware control triggers constitutive model switching, yielding realistic melting style scene editing. We illustrate the deformation process on real-world scenes. Our method achieves high physical plausibility as well as strong temporal and multi-view consistency. Our framework supports broader thermomechanical interactions. We show bidirectional phase transitions, where the object first melts under heating and then solidifies during cooling. We further showcase collisions with real scene environments, interactions with complex geometric colliders and elastic bodies, and heat transfer interactions among multiple melting objects. Thank you for reviewing.